Suppose that I get a battery that I buy from the supermarket, and I connect this up with a piece of wire. Connect this up with a piece of electrical wire to a light bulb. So let's say I find a light bulb. Let's see. I'll just represent the light bulb. Just show it as a bits of the filaments with a glass bulb around it. So if I connect this up, you know that the light bulb will glow. It will light up, and when it's connected up, an electric current will flow. Okay, now this is usually the positive pole of the battery. That's the negative pole, and we would think of an electric current as flowing from the positive pole to the negative pole. So that's our usual idea of electric current when we have an electric circuit, and we would think that an electric current flows whenever we use electricity. When we switch on the light, when we use an electric kettle, when we use our computers. Now what actually happens is that when an electric current flows around a wire, it's actually electrons in the wire that flows, and these electrons are actually negative charges that are flowing in the opposite direction. So we have lots of electrons in the wire coming from the atoms in the wire, and these electrons are flowing in that direction, from the negative pole of the battery to the positive pole. Okay, so these are the electron flow. But by definition, we say that the current flows from positive to negative pole, and if you like, it's a theoretical idea, kind of a theoretical concept. But historically, it might be because electric current was studied before the times, maybe 2 or more hundred years ago, before electrons were actually discovered. So at that time, people did not know what's actually flowing in a wire, and it was just assumed that something would flow from the positive to the negative pole. So we call this direction, this idea of the definition, the defined current, as we call it a conventional current. A conventional current, in the sense that it is officially defined to flow from positive to negative direction, but we know that really it's electrons that are flowing in the opposite direction. So this seems like a rather strange way of doing it, and it helps to understand a little bit more about what's going on in terms of the actual atoms and electrons in a piece of wire. So let's take, for example, the usual copper wire. Now, if we think about a copper atom in the wire, let's say I just pick an atom and look at it, if that's possible. The atom would consist of, let's see, a nucleus. All right, in the nucleus there will be protons and neutrons. Okay, and around the atom there would be electrons. So electrons going around the nucleus. Now an atom, the electrons have negative charges, the protons have positive charges, and neutrons have zero charge, so they are neutral. And there must the size of a proton charge is the same as the size of an electron charge. Okay, so we have I've briefly mentioned the charge of an electron before. The charge of an electron is 1.6 times 10 to the power minus 19 coulomb. The coulomb is the unit of the charge, and it has a negative sign because it's a negative charge. Now the charge of a proton, is the same in magnitude, but it has a positive charge. So in an atom, in a normal or neutral atom, the number of electrons and protons are the same, so that the resulting charge, overall charge of an atom is 0. So an atom, a normal atom, maybe not normal, but a normal copper atom would have 0 charge overall. But that's the special property of copper metal is that each copper atom can actually have one electron, can actually allow one electron to travel away from the atom and go around the metal. So that's why electrons can actually flow through the metal. Okay, this is a very special property of metals. That's why metals are conducting, because each atom can contribute what we call a mobile electron or a free electron, in the sense that it will allow one electron to roam around, to move around the metal. And usually that free electron would always be able to move around randomly, like molecules in air, like oxygen and nitrogen molecules in air. So when we connect this piece of wire to a battery, the battery provides an electric field. It provides an electric force, like that will actually push electrons, repel electrons from its negative pole, okay, and gives a force that would therefore push the electrons and cause them to move around. So the atom itself, each atom in the copper wire does not actually move. So you can imagine that the electrons, atoms are tiny, they're really small, but the electrons are even smaller. They're much smaller than the size of the atom. And the electrons are also much lighter than the proton. So just to give an idea of the of the relative sizes, let's think about the mass of a proton. So a proton's mass is let's see, it's about 1.66, I think, times 10 to the power minus 27 kilogram. So it's tiny, it's really small, it's just a part of the center of the atom. But if you look at an electron's mass, is 9.1 times 10 to the power minus 31 kilogram, and that's even smaller. If you compare the two, the electron is nearly 2,000 times smaller, lighter than a proton. To be precise, is 2,000 times, nearly 2,000 times less massive than a proton. So that's why electrons are much lighter, and it's the electrons that will move around the wire. The atoms don't actually move, right? We know that atoms don't flow around in a solid, right? Because this is not a liquid. So it's the electrons that can actually flow around, and that's why it's actually electrons that flow, right? That's why when we connect a battery to a light bulb with pieces of copper wire, it's actually the electron flow that gives us the current. Okay. But as I've said, historically, when electric circuits were first discovered and studied, that was maybe a few hundred years before electrons are actually discovered. So scientists have an idea that something must be flowing around, but it's not known what actually flows. Okay, so it was simply assumed that a current flows from the positive pole, and as we'll see in the upcoming videos, it is possible, even so, to derive formulas relating things like currents to voltages, power, charges, and so on. So for now, let me just finish up by defining currents. So current is defined as the rate of flow of charged particles. The rate of flow of charged particles, or we can also say stroke, okay, or electric charges. Now we know that electric charges are measured in terms of coulombs. So the formula, if you like, the formula for currents, if I say represent currents by the symbol I, it would be, if I want to actually think about measuring or defining a current, one way to do it would be to, or rather the usual way to do it would be to look at a certain point along the wire. Look at certain points along the wire and think about how much charge flows past this point every second. In other words, the formula would, to calculate the current, we would take the amount of charge, I call that Q, flowing past a certain point, and I would divide that by the time. Alright, let's say during a certain time, a certain number of electrons flow past this point. Then Q would be the charge of those electrons, and T is the time taken. So current is equal to charge over time. And the units for current, we know that the units for coulomb, for charge is coulomb, for time is second. So the unit for coulomb, current is defined as to be amperes. So I'll write that down as well. Now, if I take 1 coulomb, if I have 1 coulomb of charge that flows through a point in 1 second, then the current is defined to be 1 ampere. Now I should spell out ampere. Ampere is spelled as A-M-P-E-R-E. So that's ampere.